Okay, this is day 2. I'm not in the Zoom meeting room. I'm using some other software to see how this develops. So this is our brief calculus. We're going to take a look at section 12.6 and keep moving forward. So as we go through this, try your best to keep on track and on time with the homework. We will have opportunities during class time. I will have the Zoom room open. I have updated the links in Canvas, so now I'm going to want you to click on the link, the Zoom link. In fact, why don't I just show you those things, right? So you have to be logged in. So let me switch over to here. Okay, so this is our Canvas room, our Canvas. If you haven't watched the lecture for 12.5 yet, it is available right here, lecture for section 12.5. You click there. I did use a Zoom recording to do that, so it'll have a little different feel to it, but something similar. The PowerPoint is below here, so you can pull that up, and then there is linked to some a ladder problem, which is similar to one in your homework that is worked out by the Khan Academy. We do one on there. Okay, so we'll come back, and then in the Zoom room, what I've done is I've set up actual time. So for right now, when I'm recording this is Tuesday afternoon. So on Wednesday at 10:30 is when I'll come in here. I'll actually start the meeting. I'll be there. You should be able to come in here and just enter the room that way, and then you'll see Friday and all the other dates I have pre-populated through the end of the semester. So those should be there. If I'm going to play it by ear, I'll record the meetings, because anyone who has a question will work through it. It'd probably be good for everyone to see those, so you will be able to see previous meetings here. Hopefully it all works. And so anyway, here's our upcoming meetings. My understanding, I was a little jumping the gun, is that the cloud recordings, they take a little time, and then the links will become available. So we'll see about putting them there and work through this. Okay, so with that being said, let's go ahead and take a look at our 12.6. Okay, we'll play it from the beginning. So we're going to look again at further applications of the derivative, and this time we're going to look at the concept of elasticity. So what exactly is elasticity? Right. Let's use green for this, and let's clear off the screen. There we go. So we're going to look at actually two types of elasticity. First is the price elasticity, which is as you change the price of an item that you're going to sell. You change that price. If you make it a higher price, probably less demand for it, right? But it depends on how much you change it, whether the demand becomes elastic or not. We'll take a look at those. We're also going to look at the elasticity of income at the very end, but once we've got the basic concept down, the other one will fall into place. So a little bit of economics here, and again, some of you probably, well, not probably, you economics majors should know this pretty well. So it's all about what will happen if you say increase a selling price, or you could look at the same thing of decreasing it, but it's the idea that demand will go down if you increase the price. Now, occasionally with luxury goods, actually having a higher price makes a bigger demand, but most models you'll find The higher the price, the lower the demand. And what we want to do is see if will the dropping demand actually affect the revenue? Because again, if you raise the price, you're going to get more income per item. But if you sell fewer items, then that would affect the total revenue. And so as a business person, what you're looking at is not so much how much you make per item, but maybe the total income of your business. And sometimes it's better to cut your average revenue and increase total revenue, because really total revenue is generally what you're looking at or looking to increase. Okay. So they get this example when we're going to look at percentages. So if we raise the price by 1%, how is that going to affect sales? Well, it might result in just 0.5% loss in sales. So you've increased the price by 1%, but the percentage of sales lost is below that. So you will actually have revenue that should rise. Again, it all depends on the specific instances, but that's going to be. And so what we say is that this is a case of inelastic demand. It means that you change the price, but the demand really didn't change enough. So this is inelasticity, is a small change. Okay. Now if they go the other way, so you raise it by 1%, but there's a 2% drop in demand, so now your revenue is going to drop. That's what we call an elastic demand. And it's not math, it's economics. So that's what elasticity is. It's elastic if a small change in price results in a larger change in demand, and it's inelastic if a small change in price doesn't really change the demand that much, and we'll get a mathematical definition of that. It's really a ratio. Elasticity is a ratio of price, change in price to change in demand. Okay. So here's the important part. This is where sort of the math lesson starts, of being able to go through these types of questions. So we're going to start with some function. And our demand equation, the Q is a quantity. We want to think of the amount that we would sell. There's going to be some function that will determine that, f of p, and note this later. What we're going to come up with to get the elasticity of demand is we're going to take the derivative of this demand equation and multiply it by a ratio, and we'll work through getting that, but the important part is just remember, we're going to, from this equation, we're going to be looking to get the derivative of f of p. Okay, and what you're going to see is, I'll just give you a preview. The elasticity equation is actually going to be minus the derivative multiplied by the variable p, which is the price, divided by the whole function, the demand function, f of p. Okay, so they don't use exactly this notation, so I wanted you to see this here. You might want to take a screenshot or something, but this is, and I'll write it up again in this notation, but what we're going to need to do is, we're given a function, we'll need its derivative. We take the negative of that derivative, multiply it by p over the original function, and that's the elasticity demand equation. Okay, and it will give us a number, and we're going to see if it's greater than 1, it means one thing. If it's less than 1, it means another, and if it's equal to 1, it means something. So we're going to get and that's basically what we're working on. The next few slides are going to go through the mathematics of coming up with this formula. But if you're okay with the formula, the main thing is this is the one we're going to use. The steps are going to hopefully provide a description of how that formula was arrived at. Okay, but when you come to these problems, all you need to know is this equation in a sense. Okay. So if you increase a price, you've got P, and if you increase it by a little bit, that's delta P. That's the amount of the increase, right? So the percentage of increase is the amount of the increase divided by what you started with. This is just some mathematics, times 100 to make it a percentage, right? That's how we get a percentage. The same thing will happen with the demand function, okay? But we are assuming that as P goes up, that the demand will go down. So what we indicate is that the change in the demand, the amount that we will sell, is a negative value, because we would look at delta Q would be considered to be a positive or an increase. So the same type of thing is whatever the change in the quantity sold is divided by the quantity, that's going to give us our percent change. Again, we're just going to kind of keep working through this. So the elasticity is a percentage decrease in demand divided by the percentage increase in price. That's the ratio that we get when we're looking for that. And so putting all that together, elasticity is minus Q over delta Q over Q, delta P over P times 100. You do some simplifying, the hundreds will cancel out. These fractions flip, right? You flip and divide. And again, we can show all of this. This is not necessarily the lesson itself, it's getting to the important part, what we're going to use. So what you end up with is wrong one. So the way they went about this is you get minus delta Q over Q divided by delta P over P. The hundreds canceled out. You flip the second fraction and multiply, so you get minus delta Q over Q times P over delta P. And then what they did is they swapped places here. You can kind of see, because everything is just being multiplied, delta Q over delta P is equal to P over Q. Not equal, sorry, times P over Q. Okay, so that's how they come up with this part. Now remember, when we have changes, this is really a slope function, and what's a slope? It's a derivative. So we're going to see that's the derivative minus the derivative, and it's negative because the demand should be dropping. Okay. And then we get P divided by Q, and remember Q, what is Q? Q is that function f of P. So they're going to give us some function so it's going to be P divided by the function. Kind of the reverse of when we had average cost. Remember, we'd have a cost function divided by X. That's average cost. This is elasticity, which is, in this case, the X, the function is in the bottom. So a similar concept, but slightly different. And so let's now get to the major part of this presentation. Here's our main formula, and I'm going to give it to you in sort of both ways. So here, remember, this is the derivative of Q with respect to P. So we're going to take that function. We're going to take a derivative of the function. Remember, this all starts with some function that Q, how did I do that? I want blue, but I don't want it that thick. I want it there. Let's So we're starting off that Q is equal to some function of P, the demand. And so this part here is the derivative of the function. P is just the variable P, it's the price. So a lot of times when we know that particular price, we just are going to plug a number in there, and then in the bottom here is the actual function, not the derivative function, but just the function itself, f of P. Okay, so here's another way of writing this notation, that elasticity is equal to the derivative of the demand function times the variable P divided by the demand function. And we'll work through an example here. And then if the result is a number greater than 1, it's simply inelastic. Okay, it's inelastic. If it's oh wait, I got that backwards. I thought that was, it's elastic if it's greater than 1. Here it's inelastic if it's less than 1. That makes sense. Okay, so inelastic means a change in price really doesn't affect the demand so much. You're still going to get more revenue. Elastic means a change in price will actually will change the demand and thus reduce your revenue. And what we're going to see is that unit elasticity is really, we're looking for a price where the elasticity is 1, and that means it's sort of the best price we could usually get at in economic theory. Okay, that's all theory. Here's the mathematics up here, our formula, that's what we're going to use. We'll get a value that's either 1, bigger than 1, or less than 1, and then that tells us whether we're elastic, inelastic, or unit elasticity. Okay, so let's look at an example. Okay, so what do we got going here? Well, we've got a function. Remember, this is the function f of P is 20,000 minus 2P. While we're at it, you know we're going to need the derivative of this function, and that is just going to be, this is 0, this becomes, the derivative is minus 2, right? Negative 2P, the derivative is negative 2. And so putting it in that formula, remember E equals minus f of P, the derivative of it, times P over f of P. That will give us our elasticity. So notice here the negative, the first negative, that comes from the formula. The negative 2 comes from the derivative itself. Okay, taking the derivative. The P has come from the P in the formula. And then the bottom of the fraction, the denominator, is f of P. It's the function itself, 20,000 minus 2P. So what they do is they do some math. Negative and negative makes this a positive, and then 2, we can distribute it over these. The 2 on the top cancels. This becomes 10,000. That becomes just P, and so this is our elasticity function. And then what we do is we can test it at various prices to get to see what E is going to be. So one is they're asked to say, well, if the price was 2,000, what is its elasticity based upon this being the demand function? Well, we put 2,000 in up here, and you get, well, actually you get in 2 places. 2,000 over 10,000 minus 2,000, that gives you 2,000 over 8,000, and when you divide this out, you get 1/4. 2 goes into 8 4 times. So E is 1/4. That is less than 1. So when it's less than 1, that's when we say it is inelastic. Okay. We do the same thing with a price of 8,000. So, and again, in the problems, they'll give you these numbers. So we plug the 8,000 in for P in both of these places. And in this case, we get 8,000 in the numerator divided by 10,000 minus 8,000. So that gives us 8,000 in the numerator divided by 2,000 in the denominator. And in this case, 8 divided by 2, or 8,000 divided by 2,000, is the number 4. 4 is larger than 1, so it is elastic. The demand is elastic in this, at this price. Okay. So far, not so bad, right? Really just take one derivative and follow through with that formula. But, you know, this is going to be a major thing right here. In fact, let's put it in red, right? This is the major formula you're going to use. The derivative of the demand function, the negative of the derivative, times the price over the demand function. Okay. We do the same thing if you plug in the 5,000. Now you're going to have to remember what that formula was. This is why it's nice you can pull up the PowerPoints. It was P over 10,000 minus P, right? Our elasticity. So we get 5,000 over 10,000 minus 5,000, which is 5,000 over 5,000, which equals to 1. So it means at this price we have unit elasticity. And we're going to see that that oftentimes is the price we're going to shoot for. Okay. So if the price is 2,000, the demand would drop by 0.25% for every 1% increase in price. And then so if we want to see the effect on the revenue, we can use the fact that for small changes in price, the percentage change in revenue is approximately, that's what this means, approximately, very close, it's the percentage change in price plus the percentage change in demand. Okay. So let's see how that would affect things. So remember that the demand is dropping by 1/4, so that's a negative. So when we look over this, 1% increase in price results in a negative 1/4, a drop of demand by this much. So the revenue actually changes by about 0.75%. It increases by 0.75%. Okay. So if the demand is inelastic, if we raise the price, we'll increase the revenue. And that's why we want to, we don't want to sell at 2,000. Selling it for more, yes, the demand will drop, but each time we increase it, we're actually going to increase our overall revenue. So where does that stop? Well, when we get to unit elasticity, right, 1, that's where we would stop. That's the most efficient pricing for producing the greatest revenue. We're going to, you know, so it just says keep increasing the price until you get to unit elasticity. Oh, I should do it this way. Okay. So if the price is elastic, which means you've got too high of a price, and increasing the price slightly will lower the revenue. So the demand is elastic. Lowering the price increases the revenue. So this works the opposite. So when you're above unit elasticity, you need to lower the price down. And again, the one that you're going to get the largest revenue with is unit elasticity. So using this mathematics, we can price our product to say we should sell it at 5,000. That will get us the most revenue. We could sell it at 8,000 to some people, but the revenue to the company is actually going to be less than if we were to sell it at 5,000, because more people are going to buy it at 5,000. This is the market economies we play with. Okay. So here we go. Let's take a look at a new example. We're going to be given a function for baby dolls. So we've got this function Q equals 216 minus P squared. P is the price per doll in dollars, and Q is the doll sold per week. And again, if you want to think of this as a function, Q is really just the function of P. So f of P, 216 minus P squared. While I'm at it, let's go ahead and find out what our derivative is going to be. So the derivative of this function, 216, derivative is 0. So this gives us a minus 2p as our derivative. We're going to be using that. Compute the price elasticity of the demand when p equals 5 and when p equals 10. Interpret the results. Okay. Find the range of prices for which the demand is elastic. Find the range of prices for which the demand is inelastic. So we'll test those two, and if we can find the one that is unit elastic, anything above that is elastic, and anything below that is inelastic. Okay, so remember when E equals 1, we have unit elasticity. So E less than 1, inelastic. And when E is greater than 1, we have elastic. Okay. Find the price at which the weekly revenue is maximized. What is the maximum weekly revenue? So it's going to be maximized, remember, right here when we find E equals 1. So I'm sure they're going to work it for us. So, but remember, we're going to have this function. Let's just go ahead and write it out before we go over there. It's going to be minus the derivative times p over the function f of p. So in the end, we end up with E is going to be minus negative 2p times p over 216 minus p squared. Okay, so that's what we're going to be working with. We've got some prices here. You could simplify, but we could also just start plugging in the 5, plug in the 10. We'll get those found out. And then we could solve, we could set E equal to 1 and solve this equation. But let's go ahead and let them take a look. Come on. There we go. So again, they use slightly different notation, but this is the derivative, negative derivative p over q. And so minus p, right? We had that, so there they end up with 2p times p over 216, which is right similar to what we had. We had minus p minus 2p, so that becomes positive 2p p over 216 minus p squared. Okay, so that's what they've got. They simplify a bit. The p times p is p squared. Here we go. plug in 5, and we'll just let them 5 squared is 25, 5 is 25 down here. So they end up with 50 over 191. That looks like it's going to be a number less than 1, right? We know that. We know it's inelastic, but we can actually calculate it's a 0.26. So this means that increasing the price by 1% results in a 0.26% decrease in demand. Okay, did I get that right? That's good. I'm already picking up economics here. So if we have it at 5%, dropping, the demand will drop at 0.26% for every 1% increase in the price. Okay, so again, E was 0.26, it's less than 1, demand is inelastic. So what we want to do is we want to charge more than $5. Okay, we check when it's equal to 10, so let's see what happens at 10. We do the math here, so that should give us what, 200 in the top and 16 in the bottom, right? 260. Oh no, it's not multiplied by 2, so 116 in the bottom. We see we're going to end up with a number greater than 1. In fact, it's 1.72. So here the demand is elastic. $10 is actually too much. It's going to reduce the demand below, so we increase the price of 1%, the demand's going to drop by more than that, 1.72%. So there must be some place in between $5 and $10 that will work. Well, how do we find that? We set the equation equal to 1 and then solve for p. Now we've got a function here in x squared, right? So we could solve this graphically. We could graph this side as one, say y1, graph this side over here as y2, and we will be able to find that intersection point. Okay, where they intersect is the value of p that will give us the best value. So let's keep these, we'll come back to it. Here we are. Let's go to decimals. Just to get a good start on this. So what was our function? Our function was 2x squared divided by 216 minus x squared. Okay, so that's our function, our first function, and we want to find where this is equal to 1. We'll do y equals 1. And we can see there's two places. There's one over here at negative, but we don't want to charge negative money. The other one's over here, $8.49 if you want to round it up, $8.49, but 8.485 would be our preferred price. Okay, that's where it's equal to 1. Return to our PowerPoint, and we're going to take the slideshow from this spot. We got a little bit ahead of ourselves here. They did some algebra. They found that p squared is equal to 72. Multiplying probably both sides, doing a cross multiplying. So what they would have had is 2p squared. This is what they skipped. 216 minus p squared, right? They cross multiplied this times 1. This is really 1 over 1. And then what you can do is you can add p to both sides. at p squared. So algebraic way, this gives you 3p squared equals 216. Divide both sides by by 3. P squared is going to be 216 divided by 3 must be 72. I'll let you verify that with the calculator. Then you can take the square root of both sides, and the square root of 72 ends up being about 8.49. Okay, that's what we got graphically. So you do a graphical, you could do it by algebra, whichever you like, but it's telling us that we have unit elasticity at about $8.49, and that's about what we should charge. If we charge more than that, the price is really too high. The demand is elastic. Any little change we drop, we lose demand. If we go below that, then the demand is inelastic, and that's when we kind of want to change the price, keep going until we can maximize our revenue according to the capitalist system. There's other ways of looking at this, but this is what the mathematics tells us. Now, morality might tell you something else as you go to the grocery stores and you see empty shelves and such. But so how do we get to the maximum weekly revenue? Well, we know the best price is $8.49. So we take that price times the quantity function, the demand function. And what is that demand function? So again, we'll do this before we get to the next. So remember this demand function. This is f of p, which was 216 minus p squared, right, times p. This is going to give us revenue, the price, times the amount that we will sell. And what we're going to do is we're going to plug in 849 for p in each of these. Now, you could distribute through the p, you'll get a cubic, and you'll get that. But let's go ahead and see what they do. So we've got this formula. We plug in, they got tricky, 72 to get any rounding errors off. And then when you do the math, you get 144 square root of 72. And when you multiply that out, that should give us a maximum revenue of $1,222 per week by selling it at that price. You could play with it. Go back and see if you charge $5 and see what your revenue would be less. If you charge $10, plug that in there, your revenue also should be less. This is supposed to be the maximum revenue. Okay. Similar concept, we don't need to talk too much about this because we've already developed the concept of elasticity. Same thing applies to income. We will just have a different formula. Okay, so the concept of elasticity can be applied to this other situation, income elasticity of demand. The percent increase in demand for a particular item per percentage increase in personal income. So that's measuring how much people are going to demand something if their income increases, because then they have more disposable income, hopefully. And so that's another economic way of looking at things. So one is a price base, this is a income base economics. Okay. So we've got this formula here for that depends upon income. And we're given sort of the demand for so many Porsches depends upon this income function, and which is good between 1 to 10. So X is the income of a potential customer in hundreds of thousands of dollars. Wow, that'd be good. And Q is the probability that the person will actually purchase a Porsche. The income elasticity of demand is, again, you'll see really the same formula, but again, what we're using is X for income instead of price. X is the income of the individual. Q is the formula they give us. Remember, it's really a function, f of x. Could have written it this way. So elasticity is really the same as what we were looking at, except it's not, we don't have that negative. right? Because we just don't. So we get the derivative of the function, again, times x, the input variable, all over the function itself. Okay, so you'll kind of see the derivative of the function, and you'll see the function. So while we're here, the next page we'll do it. We're going to calculate the elasticity of income for x equals 2 and x equals 9. Remember, x is the income of potential hundreds of thousands of dollars. So 200,000 to 900,000. I think the person who's making 900,000 is probably more likely to buy it, but 200,000 could probably do it too. Okay, so our elasticity function is going to be the derivative here. So this derivative is, again, that's going to be a little bit of work, right? It's a natural exponential, so it is its own derivative. Then the chain rule says then we multiply by the derivative of the inside part, which is the exponent. So for the derivative part, we get 0.005 e to the minus 0.05 x squared plus x. Then we need to multiply by the derivative of the exponent. So 2 times 0.5 will give us negative 0.1 x plus 1. Derivative of x is 1. So that's the derivative. Actually, let me, I'm not going to have enough room. The derivative. So we're going to see this part, and then what we're going to multiply it by is x over this. So you're going to see that this part, this whole messy part, is going to cancel. But let's take a look at what they do. Okay, so we've got our function. They give us the derivative, and again, this second part here, this comes from the chain rule, taking the derivative of the exponent, right? The derivative of an exponential, especially a natural exponential, is itself times the derivative of the exponent. That's what that is. So we get the elasticity is the derivative times x over the demand, the income function in this case. And this is what we worked out. And again, what you're going to see is this function, because that's when we have e, this cancels each other out. So we're going to get x times this. A lot simpler. And then now we're supposed to plug in 2, and we're supposed to plug in 9, and that'll give us our two values. When we plug in x equals 2, you get 1.6. And so if we have an income of 200,000, remember that's what that 2 means, the probability that someone's going to buy that Porsche will increase a rate of 1.6% for each 1% in income. We don't know how likely they are to buy it at that level, but that's what that's telling us according to the math. But watch what happens at 900,000. I think we're going to get a much larger number, right? So we put a 9, and we get 0.9%. Thus, at 900,000, almost $1 million, the probability that they're going to purchase increases simply at a rate of 0.9% per 1%. So I guess if they've got 900,000, they haven't bought a Porsche already, a little bit more income is not going to make them more likely to buy that income, that Porsche. But at the lower level, probably what's holding back the ability to buy that is the income itself. So increasing the income, they're more likely to buy it. The high level, they already have so much income, they could have bought it. If they didn't buy it, there's something else that's needed besides income. That's how I would explain that. And that's the math lesson for today. Elasticity of demand, a lot of economics involved here. So what we will do is watch over, hopefully you've watched this, and then during class time, I'll have my Zoom room open. You can come and ask questions about how to actually apply this. So I'm hoping that this may actually increase our ability to get more done. I will have these. You can watch these at your leisure and before class, and then we have all the time in class through the Zoom room to make sure you're able to understand the concepts and the homework and apply, in this case, 12.6. Okay, so take a look, and I will see you in class Wednesday, and then on Friday we won't have a new lecture, so you have these ones, but we will still have the Zoom room open for meeting Friday at class time. All right, take care.